Hello and welcome to the C programming lecture on enums, structures, and Typedef. Okay, so what are structures? In C, structures are a way for us to group primitive data or other custom types inside of a new type. So up until this point, we've been using a lot of primitive types, things like integers, floats, chars, things of those nature. These types are nice, but typically, usually in a program, a more complicated program, you're going to want to make your own structures and have those structures have data organized in a particular way. So in other words, structure is a collection of named components, often referred to fields, that have different types. Each of the fields have their own names as well. So this field list here, you can see here's an example. This has an X and Y, both of the same type, but the structure's name is a point. So here is the usage. Here's the more abstract usage for a structure. Here's the struct. Here's the struct tag, or the name of the structure, and the field list. So once you define a structure, you need to be able to access those particular fields, these members, these things that are inside of there that we've declared. So using the concrete example of our point structure, you can see inside of this example, we have a point structure with the fields X and Y, both integers. We can declare a particular point by saying the keyword structure and the name of the structure. In this case, the structure tag is point, and the variable name is P1. So in order to access those individual fields, we just use the dot operator. So we do p1.x equals some value that we can assign to it. And we can do this for every field that's associated with the structure. You can see I do both X and Y, and then I actually output it the same way by reading them, by again accessing them. So this is the assignment of the actual individual fields, and these are reading them back out. And we can see this output here from line 15 in our terminal. So another interesting thing happens when we want to use, when we want to access a particular variable using pointers instead. So pointers to structures versus just structure. And we can see this here that, so a pointer is a structure that can be, a pointer to a structure can be created, but in order to access it, we need to use, in order to access individual fields, we need to be able to use different dereference operations. So we can see that here inside of our example on line 19, there's this arrow function. And we mentioned that in the pointer section that sometimes in order to deref, we might need to use this arrow. This is usually used when talking about pointers to structures in order to access their their fields, their particular field variables. So again, using the same program as the prior example, we're setting up the exact same code here from line 11 to 15. But then in line 17, we see that we have a pointer. So we have the variable defined as ptr underscore p1 equals the address of p1. So in order to access our x variable or x field inside of p1, we use the arrow operator and reassign that to 30. And we can see that when we output again on line 21, our p1.x and p1.y, and here our second output. So we see that these first two lines are our first two output. The next two lines, so line 3 and 4, are this line number 21, and we can see that it's 30, 20. Now, all that this is doing underneath, I wanted to show you the alternative syntax on line 23. That's the exact same thing as line 19. It's just the expanded form. So like you can dereference a particular memory address and then use that dot operation again. Now this can be a little bit complicated to do all of your code this way. Really, it doesn't matter how you want to structure it. It's most people in most code you'll see use these the arrows, but do not be surprised if you see this somewhere as well. And you can see it does the same exact thing through the last two lines of our output. We reassign the field x from p1 to the value 100, and then we re-output p1.x and p1.y. So how are structures laid out in memory? It's a great question. So each field on the structure has a particular length that contributes to the overall size of a structure. So let's just kind of unpack that statement real quick. If we have a structure that has one field of size integer, that structure should only be of the length of that one integer field. But let's say, for instance, that we have 3 fields. So 3 fields of the type integer. Recall that an integer is, in this particular instance, let's just say 4 bytes. So the size of this particular structure should be 4 times 3, right? So, and then we can see that as the memory addresses increase, that is how each element is packed in. So the last variable should have the highest memory address. So there's also something called structure padding. So depending on the CPU architecture, a compiler will be able to make a decision as to whether or not they need to align a structure on a particular byte size. This is just due to the fact that particular CPUs work better when the structures are aligned in a particular byte length. So that's going to be a little confusing. Don't worry about that too much, but I just wanted to keep you aware of what can occur. So for instance, consider that you have a structure that contains one integer field and one character field. So in this particular instance, let's assume that a integer is 4 bytes and one character field is another 1 byte. So the overall structure is the size of it should be 5 bytes. In this scenario, the compiler may choose to add some type of padding to make sure that the structure aligns to a 4 byte width by adding another 3 bytes of padding. So that way, instead of 5, you are now at from 5 bytes to 8 bytes now. So that way that you align on a 4 byte width. And again, this has to do with how memory is accessed at a lower level. This is not necessarily something that you need to be concerned with right now, but it's something that you need to be aware of. So here's an example of exactly that. We make a structure called padding. This has one integer variable and one character variable. And what we're doing here is we're going to output the size of an integer. So our first output here is the integer size, and then the second output here is going to be the character size. Now, just by what I've told you before, it should be the length should be the combination of the sizes of each individual field. So in this particular scenario, it should be 4 plus 1, which is 5. But when we output the size of the struct named padding, it's actually 8 bytes. So the reason, again, just has to do with how the compiler and the CPU architecture that you're compiling for likes to have its structure aligned. So again, just to kind of hammer home the point, what's happening here in this simple scenario is that we have a structure named padding. So this first 4 bytes is the X variable, the next 1 byte is C variable, and we actually have 3 slots that are empty here of just padding. So padding can happen between fields as well. This depends on how the compiler chooses to pack a particular structure as well. So this is, again, in this scenario, we're just assuming this is how this is occurring, but it can actually add padding between variables as well. So you can actually pack a structure. You can be done manually as well, but we're not going to get into that. But you can, there's certain operations that you can do. There's certain things that you can tell, that you can basically use indications to the compiler that you want things to be done a particular way. Okay, so moving on, what is a typedef? The keyword typedef, this indicates that the declaration of a new name for a data type rather than a variable or a function. The typedef is considered a storage specifier and doesn't introduce a new type. It's just simply aliases a particular type. So in this particular case, we have a structure and its structure tag is _point. But because we've used this typedef keyword at the beginning, it actually just aliases this. So that way we don't have to basically keep typing this keyword structure anytime we want to create a new point type. We just need to type capital point P point. So we'll see an example of this. Here's an example of a typedef. So this is showing the old way and the new way. We have a typedef structure of the underscore point structure. That's the structure tag. This is the actual typedef, so the alias. And we can see the old way here is using the old structure. We need to have it that the tag actually be underscore point. And in the new way, we just have the actual typedef. I think this should be fairly intuitive. It's, you're just creating an alias on something in order to make it less verbose. Okay, so here's another interesting thing inside of C. C provides you with something called a union. So a union is also a user-defined type. However, inside of this particular structure, all the variables actually share the same memory addresses, the same memory locations. So what does this mean? So you can actually create something, in this particular case, this is a real example that I like to use. You can union a structure in this particular way in this example. So we can create a union. That union can contain either a array of two, so like two elements inside of an array named V, or it can be a structure that contains an X and Y. And you can see that this could probably expand to other types as well. And technically, the first element of V actually maps to the same thing as using this X, and the second element as the Y. So again, these use the same memory addresses, and we'll see this in action now. So again, using this exact example that I pulled from the last slide, here is a typedef of a union. This is a vector2, and typically this is like how I like to set up some of my code that uses mathematic vector types, just because you can make things more convenient for yourself. So looking at this particular scenario, I create a new structure, or in this case, a union of vector2i, and the variable name is t. I'm initializing only the x and y. So we have x is equal to 10, y is equal to 200, and we see that we print out x and y inside line 21 and 22. And in line 24 and 25, we actually index our individual v components, or each element, which is 0 and 1, and we can see it's the exact same thing as using x or y. And this is what I mean by it using the same memory addresses. These are, because it's in a union, every member shares the same memory address. So what is happening inside of here in line 6, this is called a structure alias, or an anonymous structure. So you don't really need to define a structure necessarily. You could break this out and somehow union this, and that would work too, but this is just a convenient way, so that way you don't have to have like multiple types floating around. And you can just use some type of anonymous structure here. Okay, so moving on next to enums. So in C, the keyword enum stands for enumeration, which are user-defined, user-declared types. Enumeration is a set of integer values that represent basically just constant enumerated values, so like integers. So normally you'll have a word or a particular variable name associated with this constant. So here's a pretty concrete example of color. We can say that color has three enumeration values inside of it. There's red, green, and blue. Red equals 1, green equals 2, and blue equals 3. So here's an example of exactly that enum. So we typedef it, we make it underscore color, and then we have just lowercase color. So we can actually do using the same type of thing here. We have we have to explicitly define the enum here as C1 equal red, and we can see we output that particular value, which maps to 1, which is exactly what it is on line 5. And then we see on line 13, C2 is green, which green should map to 2, which is on line 6. And we see that exactly on our output here on line 16. This should be fairly intuitive as well, because up until this point, it looks pretty similar to a structure. It's just these particular types. We don't have to do like color.red or any of that. We just say red and it knows that we're using this particular enumeration. Okay, in order to recap what we just went over, a structure or struct is a user-defined data type that consists of other declared or primitive types. Structures are just a particular way to organize data or group data together. Each field of a particular type can be accessed by adding an offset to the structure's variable memory address. So that's another important thing to recall, or thing to remember, is that we can just use an offset at that particular memory address for that particular variable of that type and access each individual member or field. So enumeration is a user-defined data type that contains enumerated constants, just integer values. A typedef is a way to alias a particular type. We've seen instances where we typedef unions, structures, enums. Typedef is very useful for other various things as well. All right, so union. Again, creating a union just unions all the fields inside of that particular union, and they all share that same memory address. So another way of thinking about it is that the fields really just become aliases for each other. So that's a particularly useful way of thinking about it. All right, so in this particular lecture, I want you to work on a exercise. So I want you to create a list data type that contains an int field, name data, and another field of a particular pointer to that same type or structure that is currently being created, named next. So after you create that structure, I want you to create 4 individual variables of that particular type that contains a different number within that data field. I want you to link those together. Now, after you're done, I want you to create a loop that will go from the first to the last item in that list, using the next pointers to the structures. Upon completion, that program should terminate. So just showing you what this may look like, here is a diagram of how you can kind of conceptualize this process. So the first structure here at the top of the list, maybe this is the address as at 1, the data is 301, and the next pointer points to the address of 0x02, and we can see that that points to this one, and we see that has different data associated with it, some numerical value, and we see that its next pointer address is actually 0x03, and that points to this next pointer variable, and this value has some data inside of it, and it points to this address, so 0x04, and we can see that the next field is null. So that's how we know that we're at the end of the list. So just try your hardest to kind of work through this stuff. We're actually going to do this together inside of the coding portion of this lecture. But before you get into that and before you look at my solution, try it yourself and just play around with the code. That's how you'll get better. Okay, let's go ahead and go over the exercise that we assigned in the last lecture. So in this particular lecture, I was basically asking you to create something called a linked list. Now, a linked list is a particular type of data structure that is particularly useful in certain scenarios. I think it's pretty interesting little data structure, especially when you're first starting out, because it just kind of elevates your thought process to another level of understanding in code. So let's go ahead and start out with just making our main.c file. Go ahead and open up this main.c file inside of our code editor. And we're going to go ahead and just write our standard hello world program to get started. Okay, GCC may not see, compile, there we go, everything's working. So first things first, let's go ahead and declare our actual type here. So we'll do type def structure, we'll name it a node. This is something typical that you'll see people do. Again, we had a data field, let's say it's an integer, and then the next field is going to actually be our node field. So we want, because the alias will not work at this particular point, unless we typedef it before, which is another topic for another day, we're just going to go ahead and use the structure tag name, and we're just going to put next. So in this particular example, we're going to create our first node by saying node, and we'll just say node underscore 1. So this is going to be our first node, and we could actually say something along the lines of like head or something like that, but 1 is fine for our particular use case, and we can explicitly set data equal to, let's just say 1, and the next variable perhaps is equal to, let's just say null for now. So, oops, these need to be commas. And there we go. Okay, so everything compiles. There's no output right now, so we don't have to worry about that. Next, let's go ahead and let's just output our, so we'll say node, and then we'll just do a %d, because we're going to reuse this. Let's say node %d, value %d. We'll say node address %d, node value %d, and then we'll just say next %d, something along these lines. Actually, let's use a pointer /n, and we can basically reuse this when we get into our looping statement. So, all right, so node 1, we're going to go ahead and say we want the address of that. So there we go. We're going to want the value, so we're going to go node1.data, node underscore 1.data. And the next thing we're going to do here is say node1 dot next. So what we should see for this particular output is the address, the value 1, and then nil or null. But in our output, it will say nil. Okay, perfect. So this is setting us up. So this is actually needs to be a P as well. And there we go. It looks better. So perfect. So what we're going to do is let's create a few more nodes. We're going to basically use the same thing. So let's just do like 2 more, and let's just lower this window a bit so we can see what's going on. All right, so we'll say this is node 2. Let's say this is 2, and then our next pointer is actually going to be equal to, in this particular case, we actually cannot, let's just set them all to null for now. Okay, so they're all null. Now what we want to do is link these together. So what we can say is, let's put this 3, and then data is 3. What we can now say is node1.next is going to be equal to the address of node 2, right? So now this is storing the address of node 2, and now what we can say is node2.next is going to be equal to the address of node 3, right? So what inevitably happens is that just like our diagram that we showed, we are chaining these together. So what we can do now is let's create a node pointer. Let's set that to our address at node 1. Okay, so while the pointer does not equal null, and this is our looping statement, we're going to print out this particular variable here. So we're going to say PTR, which will be our actual address, and then we're going to say PTR pointer to the data, and then we're going to say, okay, the next one, PTR next, right? So what needs to happen is that we need to say, okay, the pointer is going to be equal to the pointer next variable. So what should happen here is we should see the output from node 1 to node 3, and then it should terminate. So let's go ahead and run this program. Okay, so the problem that we have here is that we put next.to, so this is node2.next, GCC may not see. And let's expand this because I want to make sure that we're able to see that. No doubt. And that's exactly what occurs. So if you could, let's kind of reason about this again. So the node address is, this is our first node, right? So our first node has a value 1. This is exactly what we expect. Our next variable points to node 2. Node 2's address is here. Its next, which is value is 2, and then its next is this particular value, which is on node 3. And node 3 has a value of 3, and it points to nil. So we can actually change this stuff to like -100. Maybe this is like 2000. And up here, maybe this is like, I don't know, let's say 4. And it doesn't matter. You'll see exactly this is what we expect. The first node's 4, the next one's 2000, next one's 100. So again, the structure is called a linked list. You can look this up and figure out how different ways to implement it. This is just one particular way of implementing a linked list. This is, when you think about it, it's kind of an alternative to an array. Arrays are good for fixed sizes. These are expandable and shrinkable. Now, that being said, there's other problems with them as well. Data segmentation and all this other stuff. So anyways, this is how we would create a very basic linked list inside of C. I hope this kind of gave you some insight and you kind of got close to this particular structure in your program. If you didn't, it's okay. At least follow through and write all of this code and just tear it apart and make sure you understand what each line is doing. That in and of itself will help you. All right, great. Thanks for making it this far. Hope to see you in the next lecture.